Alright, we're gonna run through how to do number 2. I'm gonna have to talk out loud because there's a lot of interference in this room. But this is the general setup of the problem. We're told that wires are coming, the current from the wires is coming out of the page. So what that means is that drawn here with a dot, that picture current coming out like this, and the field surrounds the current within the plane. So if it's represented with a dot, think of it like it's an arrow coming towards you. That means that that's coming out of the plane. If it's an X, that's like the back of the arrow going into the plane. In this case, we only have going into the plane, or out of the plane. So, the field is going to be around that. And you're going to use a version of the right-hand rule on all 4 of these. So, if it's coming out of the board, your thumb is going to represent the wire. Your fingers are going to represent the field. So if it's out of the board, counterclockwise. Into the board, clockwise. So up here, we're going counterclockwise. So think of this as going entirely around. In this case, what we're going to do is represent this just by 4 field vectors for each of the wires. And just to label these, this is wire 1, this is wire number 2, 4. So these are 4 wires, these are the fields for each one. They're all going in the same direction with respect to the wire in a circular manner. So again, imagine these arrows could be drawn anywhere on here so that they were circular. Now for the problem, we're given to find the electric field vector, or the magnetic field vector, in the center of the square. So that's where we can draw a vector diagram. There's our center. And if we start with 1, we figure out where 1 would intersect. If you extend this circle, it's coming out at this turn here, so it means it's going to be going up in that direction. So I have to visualize that. So B1, remember these are the electric field, going up in that direction at an angle of 45 degrees. Because this angle here would be up there. So hopefully you can see how that's shown. Again, this is circular, uniform. So when it's down here, it's going this way at 0 degrees. When it's up here, it's going 90 degrees. In between, coming off about 45 degrees. So you can extend that. You can imagine the circle getting larger. And then we do that for all 4 of these. So for 2, it's going around like this. It's going up like that. This should be 3. Sorry, not 4. For 3, we're going down like that. So 3, B2, and then for 4, it's coming in like this. B4, and again, these are all 45 degrees. Alright. So now we have our 4 fields. And what we want to do is figure out what the net field is. So this is all just vectors. So if you got this far, if you're comfortable with that, then you're comfortable with everything new about magnetic fields. All we do now is figure out the strength of 1, 2, 3, and 4 and add them up. This is the formula we're going to use. It's similar to the electric field formula. Remember, E was KQ over R squared. This is fairly similar. But we're using this one. This is at the bottom of the page. Remember, write this on your formula sheet. K prime is 10 to the minus 7 Teslas meters per ampere. That's K prime is there. Now we do this for all 4. Now the current for 1 equals the current of 4 equals 10 amps. And for 2, it equals 3, and that's 5 amps. So we have 1 and 4 are the same, and 2 and 3 are the same. So visually, we can calculate 1 and 4 using the same thing. B1 equals B4 will equal 2 k prime, I for either 1 or 4, it doesn't matter which one we use, over r, and the distance is going to be the same. They're all from this distance from the point. Now the question is, what's this side length? So if I just quickly redraw this square, just for clarity, 1 meter, 1 meter, so that Pythagorean theorem, this is 1 squared plus 1 squared, square root of that, so this is radical 2. So half of that here is radical 2 over 2. This is radical 2 over 2, this is radical 2 over 2, together they're radical 2. So your r for all these is radical 2. So if I plug in all of my numbers, where I is 10 amps, r is radical 2 over 2 meters. This comes out to be V1 equals V4 equals 2.83 times 10 to the minus 6 Teslas. Magnetic fields are in Teslas. Okay. So I'm going to assume that you've got the answer here, so you can calculate this for 2 and 4, just to save on time and space. So if you've got this down, this is something that the key, remember, I've shown that. We're able to go that far. Now we want to do the summation in the x and in the y direction. Now think about it. These two are equal, right? So this the up component of this, the y component, will equal the negative this. So they'll cancel. Same with over here. 2 and 3 will have equal fields. So these will cancel. So this is 0. There's no field in the y direction. So all we need to do is figure out the field in the x direction. So if we want to do 1 and 4, that's 2 times v1 or 4, doesn't matter, they're the same magnitude. And a cosine of 45 degrees will give us our x component minus 2 b, 2 or 3 goes over there, cosine of 45. Plug that in, get your number, you'll get the summation of forces in the x direction, the summation of fields, magnetic fields in the x direction, equals 2 times 10 to the minus 6 Tesla in the I direction. Remember, this is in the x direction. So we can figure that out, x or I direction. Since there's no y component, this is our answer. Hopefully that was clear. I've never tried this before, so let me know if you still have questions, and I'm going to send this to you now.